AKANE SANO from Rice University. AKANE and I overlapped in grad school. We're same labs. Always a pleasure to introduce an academic sibling. Go ahead.
Thank you, Isan. Hello, everyone. My name is AKANE SANO. I'm an assistant professor at Rice University. I'm presenting this paper for my student, Han Yu, who couldn't make it, unfortunately, due to his visa issue. So today we're going to talk about a semi-supervised learning framework for momentary stress detection, but we believe that this framework can be applied to any other similar setting with a limited number of labels. So first of all, let's talk about why stress detection is important. So as everyone knows that stress, we have a lot of stress in daily life, and there are many pros and cons of stress. Sometimes stress can make us very productive to finish some work, but too much stress can be problematic for both physical and mental health. And how can we measure stress and also help people manage it in a timely manner? So in this paper, we are talking about stress detection using physiological signals. So as you can see, there are potential many different devices who might be able to use. And then we are using some machine learning model. Then there are a lot of discussions how to measure stress, how to assess stress. But in this paper, we are deciding we are using self-reported stress in a binary class setting. But there are many, many challenges in stress and also mood sensing in general. And one topic we want to talk about in this paper is we have very limited number of labels. So think about our sensors. So sensors can continuously monitor data, multimodal data, so we can get 24/7 continuous data. However, it is quite expensive to get user labels. So in this setting, I'm talking about self-reported stress levels. So we will be able to provide some prompt through ecological momentary assessment for asking people how people are feeling, also how stressed are you, etc. But we won't be able to bother too much users by asking like that. Then we have some common approaches to deal with this problem. For example, we can keep only labeled data, that's some data with labels. Also, we can downsample features and data, or we could also apply define some time windows and use some sequential modeling for this situation. However, we have a lot of unlabeled data in our setting, and so in our paper, we primarily focus on how can we leverage a lot of unlabeled data we collected in the study. So next I'm going to talk about our method. So first method I want to introduce is pseudo-labeling. So as you know, stress response can be gradual. So even though we have some momentary stress responses, that doesn't mean that you are feeling stress only at that moment. So that means we can define some time windows, like time t, before and after that momentary moment. And we can label that window of t as the stress levels. Then we decided to include this parameter t in our modeling so that we can automatically learn the optimal t within machine learning models. We also use a two-stage semi-supervised learning framework where we have stage one. We use unlabeled data to pre-train a neural network model using decoder and encoder framework. But we also wanted to specifically active sample some meaningful unlabeled data instead of using entire unlabeled data we have. Then after that, step two, we will be using some pre-trained model in a supervised manner and using consistency regularization technique and feeding both unlabeled and labeled data to the model. So the first step, we have a lot of unlabeled data from sensors, and it's not all unlabeled data might not be helpful for detecting stress. So we decided to look into distribution of labeled data and both unlabeled data. And we found some distribution differences in unlabeled and labeled data. And so we applied some clustering techniques, for example, Gaussian mixture model or k-mean clustering, to understand the distribution of labeled data so that we can actively sample some unlabeled data close to labeled data. We also use consistency regularization technique. So this is the technique that allows us to learn robust models using unlabeled data as much as possible. Then here, as you can see, we can feed original sensor data in the model, but also we can apply some data augmentation, for example, adding some noise to data. Then we can also get another prediction, for example, stress level prediction 2. Then these prediction 1 and 2 has to be very similar because they are coming from the original same data set. So we use this kind of relationship within training a model using only unlabeled data and also actually labeled data both. So in our setting, we have this kind of loss function with 3 terms, and including some terms for consistency regularization for labeled data and unlabeled data. So we conducted our evaluation using 2 data sets. So both of them are using wearable and mobile sensors for measuring stress, and one data set is coming from Europe in Belgium, and the other data set is coming from shift workers, medical professionals collected in the US. Then we conducted our experiment using subject-independent cross-validation. So our results, first result is about active unlabeled data sampling, and we found that this method is very effective. And instead of using entire unlabeled data, we can effectively sample some portion of the unlabeled data so that you can see some improvement in model performance. But also, this is very, very computational efficient because we don't necessarily need to use entire data set, but we can only use a portion of the unlabeled data. We also compared our framework, semi-supervised framework, with a lot of baseline, also state-of-the-art techniques in semi-supervised and self-supervised models. And what we found was the combination of active learning, active sampling, also pre-training the model, and consistency regularization shows the best results. We also conducted several different ablation studies. For example, for pseudo-labeling, we were wondering what kind of time window would be the best for stress detection. And we found out, for example, 10 minutes and 15 minutes were the best. And another ablation study was not only stress recognition, we also tested our mechanism on activity recognition tasks, which is a very commonly studied in ubiquitous computing. And we found that our strategy can still work, and also is competitive as other state-of-the-art self-supervised and semi-supervised setting. But we found a very clear difference between stress recognition task versus activity recognition task. As you can see, stress or mood detection task is quite challenging. And we have much, much lower performance than activity recognition task. That means if we want to use that model for generate some labels, to generating some pseudo labels, actually it is quite challenging because we have a lot of errors in generating labels. We also compared semi-supervised learning versus self-supervised learning, and self-supervised learning is a technique using only unlabeled data, whereas semi-supervised learning is using both labeled and unlabeled data. And in our experiment, we found that actually semi-supervised learning works better. So with a little bit amount of labeled data, we can constrain the model in a better way compared to just learning the model with unlabeled data. So that is the summary of our work. And we also conducted cross dataset evaluation as well. But actually, our framework didn't have any specific framework to adapt distribution shift. So that is something we are also working on in our future work. Thank you very much.
Hi, AKANE, thank you. So I'm curious, how did you label the unlabeled data? Did you have binary classification, stress, not stress? Did you label the unlabeled data as 0, 1?
Yes, so yeah, originally we have binary labels, non-stress versus stress. Then for labeled data, so depending on which method we are using, for example, we could generate some pseudo labels out of supervised model we learn. But also, as I explained, we don't necessarily need to actually generate pseudo labels. So we can use consistency regularization. So that doesn't actually include pseudo label, like supervised model-based pseudo label. But I'm not sure I'm answering your question.
So I just, when you label the data, use unlabeled data, did you use also the binary, or did you use a range of?
So in this setting,
values?
yeah, it is binary, but I think similar this framework could be also applied to continuous setting as well. So we just tested this in binary for just simplicity, but this can be applied to continuous labels.
So
as well.
I'm just
well,
curious.
I think we're going to try to have to wrap up.
Right.
Let's come back to the panel
Thank
discussion.
you, Asana. Yeah, we can talk more later. Thank you very much.
All right, we have 2 more presentations left. This is the final.